is criminal to teach a man not to defend himself when he is the constant victim of brutal attacks.
In my studies, I'm trying to find out how these tiny cloud droplets can combine together to form raindrops. This sweating glass is a simple illustration of our thinking. Let's look at it in time-lapse photography. Have you ever noticed how at first the glass sweats uniformly with tiny droplets distributed evenly about its surface? In a few places, though, larger droplets form and start to fall down the sides of the glass. As they trickle down, they grow still larger by merging or coalescing with numerous smaller droplets in their paths. The question is whether this sort of thing can happen in an actual cloud. The important thing to remember is that these cloud droplets are extremely tiny, smaller even than these particles of chalk dust. These dust particles hardly seem to fall at all. It's the same with cloud droplets. They're so tiny that it would take them roughly 10 seconds to fall across this light beam. In a cloud where the air is usually rising, they may actually be carried upwards. But not all droplets will be carried upwards at the same speed, because not all droplets are the same size. So in a cloud, this relative motion of droplets may allow them to collide and coalesce, growing large enough to fall out of the cloud. The problem, as Pat Squires indicated, is that the vast majority of droplets are quite small, too small, in fact, to start this collision coalescence process. So the critical problem is what happens when two droplets come close together. We can illustrate this on a much larger scale using this tank of oil and large water drops. The resistance the oil offers to these large drops simulates the resistance the air offers to cloud droplets, which are much smaller. In fact, if we could put ourselves on the same scale as cloud droplets, this is about the way a small volume of cloud would look. The speeds with which these drops fall are very close to the speeds with which cloud drops fall in air. Now I'll release a small drop and follow it with a larger one. Here it is again. The larger drop falls faster and passes the smaller one. Note that the large drop doesn't touch the small one, but pushes it out of the way. This time watch and you'll see the smaller droplet roll around the larger one. We believe that cloud drops of the proper size can coalesce in air, but we cannot make these larger water drops coalesce in oil without introducing another force, electrical in nature. The atmosphere, and clouds in particular, carry electric charges, as you well know from seeing lightning. These electric charges and the electric fields they create may have an effect on the coalescence of cloud droplets. Let's see what this effect might be. I will place an electric charge on these plates so that there is a vertical electric field between them, similar to that exists in clouds. Now, when I form two drops, they collide in an electric field. And you see these drops coalesce. When the electric field is applied, they coalesce nearly every time. The question is, do things happen like this in the atmosphere? This is a hard question to answer. It's not easy to see cloud droplets actually collide in the air. They're so very tiny. But we can see larger water drops collide in the air. These are hypodermic needles which we vibrate at a constant frequency with small radio loudspeakers. This breaks up the streams so that individual droplets collide in front of the camera. Here we see the drops in slow motion. Some can be seen to bounce off and others to coalesce. If we apply an electric field with this electrically charged rod, many more coalesce, as you see here. Now the field is off, and again they tend to bounce off one another more often. Let's try this again with the electric field. The droplets bounce because of an extremely thin layer of air between them. The electric field provides a force of attraction between the drops, causing the water to break through this thin layer of air and allow the drops to combine. With the proper conditions, which have to do with the flow pattern around the droplets, their size, the presence of electric fields, and other effects we don't fully understand, drops do collide and coalesce. In a cloud, this happens on a gigantic scale, with drops moving up and down with the air currents, hitting each other, sometimes bouncing and sometimes merging. On the whole, the big drops get bigger and bigger as long as there is more cloud to fall through, until from the base of the cloud it starts to rain.